All right, class, we're going to get started. Okay, so I'm not quite done with grading your quizzes, the most recent quiz. Hoping to have that done on Wednesday, so we'll talk through the answers to the latest quiz on Wednesday. As a reminder, our last quiz, quiz 7, will be held during the final exam period in this room. It'll also be an hour long, just like all the previous quizzes, and it will count the same as the previous quizzes. Any questions on that? Yeah.
Well, you know the grade
I will not know the grade cutoffs before the final quiz. So I'll make the grade cutoffs determined once I factored in all the grades, including the final quiz. Yeah. Any other questions on that? So yeah, go ahead. I never said a guarantee. Yeah. I'll abide by what's in the syllabus, but I never had a specific guarantee on one grade level or another. Yeah. So the other thing is about homeworks. So originally I had a homework scheduled for today, but then I reorganized the lectures a little bit. Sorry, I originally had a homework that was scheduled to be due on Wednesday, but then I reorganized. After reorganizing the lectures a little bit, we ended up not covering any new material between when homework 12 was assigned and when I would have assigned a new homework 13. So as a result, there's no homework due this Wednesday because there was no new material to be covered on a homework due this Wednesday. But there will be a final homework assigned this Wednesday covering materials that we've done since homework 12. So basically it's going to be this quality control type material. Any questions on that on homework? So no homework due this Wednesday, but there will be one more assigned. Okay, and then as far as where we're going for the rest of the semester, so we have a few lectures, 21, 22, and 23, that are more or less on methods and quality control that are going to take some of what we've learned about different distributions. So today's going to be normal. On Wednesday, we'll talk about chi-squared, and at the end of Wednesday and beginning of lecture on Monday, we'll talk about Poisson distribution and how we can use those distributions to understand and track the outcome of some kind of process that we have that's underway. So these are also we're talking about control charting and its application to understand variance in a process and understand when a process that you're interested in monitoring is potentially going out of control. So we have those lectures coming up. We'll also go over, as soon as I have the grading done, we'll go over the results of quiz 6, right? We'll go through all those answers. And then we'll have some review. It's likely we're going to have, so we'll have at least one entire class period for review a week from Wednesday. And a portion of lecture on Monday will also be spent on reviewing the course material, because I don't think we're going to spend an entire lecture period on that last element of QC. So that's where we're going. Yeah. Nope, quiz 7 only covers material since quiz 6. Quiz 7 is the same weighting as previous quizzes, and it covers the same timing as previous quizzes, only covers that, yep. Now you'll see that we have many of the topics that we've covered throughout the semester are covered on quiz 7, right? So for example, Poisson distribution, we talked about that on the first day of class. Will be something that we're talking about on the last day of class, right? The normal distribution, which we introduced and have talked about throughout, is something that we're going to be talking about today, right? But as far as the structure of the questions, you can expect questions on just the material since quiz 6 to be covered on quiz 7. Yeah. Other questions? Okay. Was there another question, Kenneth? Do you have a question for a second? Okay, got it. Okay. All right. So then. So today we're going to talk about control charts for what's called process location. And we'll see this is mainly about if we want to know, if we have some process, for example, some kind of manufacturing process going on, and we want to track the average of some measurement from that manufacturing process to know if there's something going wrong, we call that tracking the process location, like the location of the average of what's happening in the process. So this comes from a different textbook than the I guess the primary recommended text for the class. And so again, that chapter 16 of the text from which this material comes from is up on Canvas in files, if you want to take a look. But so the idea is that whenever we have some kind of process going on, there's always going to be, let's say we're making a measurement to understand what's going on in that process. There will always be random noise, right? There will always be day-to-day fluctuations or run-to-run fluctuations in that process. But occasionally there will be a problem happening that we want to know about so we can identify it and fix it. And so control charts give us a way of tracking whether or not the variation that we're seeing in a process outcome is due to random noise. And so it's something that should be expected, or if it's something that we should maybe track down, right? So some kind of problem that we might want to track down. So as one example, using a similar method, so Micron, notice that the quality of their wafers, misspelled, was declining at some point. And they eventually tracked that down to being to occurring when there were strong northwest winds, right? So the kind that accompany the passage of cold fronts in winter. So this is the type of thing where, if you're tracking some quality outcome on wafer production, right, as Micron would be doing, if you notice that that quality is declining or just going out of spec in either direction, then or just going out of what's expected in either direction, then by tracking with a control chart, with a well-validated control chart scheme, you could then be alerted to a possible problem. In this case, they were able to track it down to something having to do with the weather outside, right? So the first step, though, is just statistically, is what we're seeing explained by random variation. And so as usual, we'll go through this in terms of an example. So the example here, and it comes from that textbook chapter that I noted, is about motor oil viscosity. So let's say, so we have a lubricant manufacturing facility that is drawing and analyzing 3 samples of oil every single day. And this is pretty typical of a quality control procedure. You might take some small amount of material off the line or some small amount of product off the line and run it through a QC lab, or run it through some tests in a QC lab in order to track what's going on in your process. And so we're given data that was obtained over the course of 25 days. And we're asked to look at the characteristics of this and plot it on a control chart. Some notes about this is just trying to guess what the units of this thing is. The units aren't specified, nor is the temperature. And since the viscosity of SAE 10W40 oil is about 12 centipoise, it's close to the values found in here. It looks like these values are in centipoise. So again, we're going to read our data in. We're using pandas to read the data in. This is what it looks like. We'll see that for each day, numbered 0 through presumably 24, we have the 3 measurements from each day recorded. And again, this is pretty typical of what you might do if you were monitoring this on a line. So what we're going to do is we're going to add some columns to the data frame that track some different parameters about the data. The most important of which for our case is going to be X bar. So what we'll see is that the kind of control chart that we're going to discuss here is often called an X bar control chart, because we're tracking X bar, or the mean of the samples, as a function of time. So we're going to add those columns that include sample mean, the day, numbered starting at 1 instead of 0, standard deviation, and the range. So there's just some notes about how we can define the operations when we're using pandas. So this is our resulting data, right? So now we have a column for day. We have our viscosity measurements, we have X bar, we have the standard deviation on that day, and then the range. So the basic idea of this X bar chart is that we're going to plot X bar, right, the average that we saw, as a function of the number of days. But in order to do that, we first want to put that result in context. So if we just make that plot, I'm going to scroll down to what the plot looks like. So if we just make that plot, so this is a plot of X bar right? The mean of that sample, the three sample values that were collected on each day, as a function of days. And right, so the red dots show the data, right, over those 25 days of measurements. And one of the purposes of control charting, right, so let's say we have this data, we want to put it in context. We want to understand, like, that excursion that we saw on day 18, right, that really high value of viscosity. Is that because of something that's going wrong or something that's systematically happening in my process that I might need to address? Or is that just due to random chance, right? Is that just due to random variation from day to day within my sample? And so more or less the whole point of this control charting is to figure out what these upper and lower limits are, which are the lines shown here, and we'll talk about where those come from, that tell us something about how probable it is to see a result that is that extreme, if that makes sense. So, so far we've just constructed X bar as a function of day, and if we were to plot that, we'd see all this variation. Now the point is, should we be worried about those high excursions in terms of the viscosity? And the way we're going to define this is by using what we know about probability and statistics to set some limits on what we expect to see within this sample. So let's say we're going to start by assuming that we know what the process should look like. And now note, this is not what do we desire the final, this is not saying what we desire the final product to be or what the specification of the final product is. It's just what does our process for producing that product look like? So here we're saying that based on experience with the process, we know that the mean is 10.5 centipoise or whatever units it was, and standard deviation is about 0.18. Like that's what we should see within this process, is a normally distributed random process with a mean of 10.5 and a standard deviation of 0.18. Now separately, like let's say we're providing this motor oil to an OEM manufacturer or something for use in their equipment. And they specify that they might have different specifications. Like they might specify that the viscosity has to be lower than 12 centipoise, right? So they might have an entirely different specification. So these numbers here, the mean and standard deviation, that's just based on that's capturing what we expect to see if the process is running as expected. It's not necessarily related to the performance specification that we're trying to hit with that process. Does that distinction make sense? So we might have, right, we might be engineering a product to a certain quality or to a certain, let's say a certain viscosity. And we would separately be running tests to make sure that we are hitting whatever that minimum spec is so we can sell that product. But here, what we're concerned in is not whether or not we're meeting a minimum spec on the product, but we're just concerned with, is our process line, is our production line running as we would expect? So so come back down to the data, right? We're going to define what these upper and lower control limits are. They're going to be based on probabilistic estimates based on how the product line is running. But let's say for this particular product, we need to have a viscosity below 12 centipoise, right? Like that's what we are trying to hit in order to be able to sell it. Notice that limit, that specification doesn't enter in here. What enters in here is based on what we know about this process, right? We know that the mean is 10.5 and the standard deviation is 0.18. Based on what we know about this process, is this process running the way that we expect it to from day to day with normal variation from day to day? Right, so these numbers, the mean of 10.5, standard deviation of 0.18, this comes from how the process runs if everything is under control, if everything is running as usual. And it may be entirely distinct from what the minimum specification is in order to actually produce or sell this product. So we're going to assume that in this case, we know based on experience, that the mean should be about 10.5, standard deviation should be 0.18. And we assume that our random variable, our measurements, have a normal distribution. So then we can use the normal distribution curve in order to assess probabilities that we see results that are located far away from the mean. And so we're going to use that to set up those upper and lower limits on our control chart and tell us whether or not there's anything to worry about. So so in this case, we're going to say that the expected value of the means that we see is mu, is the overall mean of the population, right? So now we're back to considering, again, the difference between sample, right? So we have a sample on every day of 3 measurements versus the overall population, right? Sample mean we write as x bar, population mean we write as mu. And then based on a sample size of a sample of size n, in this case n is 3, we know that the standard deviation of the sample means, or the standard deviation of x bar, is the standard deviation of the underlying population, in this case sigma, divided by square root of n. Again, call back to material from quite a few weeks ago. So given those two values, right, the expected value is mu and the standard deviation is sigma over square root of n, we can then define a probability that our result is within a certain distance from that mean. And in this case, we're going to do it in terms of the z-score, right? So remember, the z-score, we're talking about normally distributed random process, that z-score is the value minus the mean over the standard deviation. So what we are often going to do in control charting is look at our z-score limits of -3 to +3. We'll talk about where those come from in a second. So when we use z-score limits of -3 to +3, and the reason is that then if we look at the norm.cdf of those two z-scores from 3 to -3, what we see is that 99.7% of our expected values of the sample mean should be located within 3 standard deviations on either side of the mean. So what this is telling us is that if we use a z-score limit from -3 to +3 on our control chart, then 99.73% of the time, if our process is in control, meaning that things are going as expected, our process is performing as expected, then the sample mean would fall within this range of 3 standard deviations. So this is what we typically use in control charting for our lower and upper control limits. So we call this a 3 sigma control chart because we're going 3 standard deviations or 3 sigma on either side of the mean. And then in that case, our lower control limit is the mean -3 times sigma over square root of n, where n is the number of samples we're taking. My upper control limit is the mean plus 3 times sigma over square root of n. Okay. So note here, in this case, n was 3. Right, so that would be here. But this 3, this leading 3 here, this refers to the z-scores that we're using on either side, right? So even if we had 4 samples, then n would be 4, but we'd still have 3 right here because this defines how many z-scores, how many standard deviations away from the mean we're going to allow before we flag that there might be a problem. So this type of plot where we plot the mean plus or minus 3 standard deviations away from the mean is often called a 3 sigma chart. Okay. And this is what we're going to be plotting. So so this code, I've shown you the plot. This code more or less generates that plot. And you can see here that we've defined our lower and upper control limits consistent with those equations 4 and 5. Where again, sigma, this is the standard deviation of the underlying variable. But since what we're plotting is not the underlying variable, we're plotting the average, right, or X bar of a certain number of measurements, in this case 3. The expected standard deviation is sigma over square root of n. And then we're going to plot that data as shown here. And so this is, again, what we've been looking at, where now the red dots, again, are X bar as a function of days, or the average of my sample of 3 per every day on which I ran it. The dashed line in the center there, that shows the mean, or the expected mean, in this case of 10.5. And then the lines on top and bottom show the upper and lower control limit, basically. So what this is telling me is that if I see so I expect that if my process is in control, 99.7% of my values, 99.7% of all of those red dots should lie within that line. So what this means is that I'm very unlikely, like with this kind of chart, if I'm using a 3 sigma chart for my process, I'm very unlikely to get, a false positive that there's something going on. We'll talk a little bit about how well we're able to detect deviations from the mean later. But one thing that's useful about this is that we have a very low rate of false errors. And from this, the interpretation would be that since all of the X bar values are within my control limits, even though we had these relatively high excursions, we would conclude that we had stable operation over the 25 days that are reported here. Okay, so that's how we would read this control chart. Yeah.
So can you change that 3 standard deviation limit?
Yeah, so the question is, do we change that 3 sigma limit? So that's going to vary very much. It can vary from process to process. This is like, what we're going to get in these 3 lectures is an introduction to some basic concepts in quality control that you may encounter, right, when you're out working. Or that, even if you're not in like quality control or specifically responsible for quality control, you may see something like this. And so this is more just like an introduction to something you might see in the future. There will be, so this is kind of the most basic form of a quality control chart you might see. Yeah, but there are variations depending on the process, depending on, I don't know, if you're at a workplace that's implemented 6 sigma, there are other charts and things you look at in order to evaluate that your process is within spec. But note that if you had a process that is more tightly controlled, then these upper and lower control limits, because they're based on the standard deviation of the results of that process, they would come in then as well. And so then you would have a tighter limit on that outcome. So it is somewhat self-correcting, and that's why this is often a starting point. The text, for example, notes that in something I didn't know, but in Britain, the common limit is 3.09, plus or minus 3.09 sigma, which just gives you a nice rounder number of 0.025 probability of excursion outside. But yeah, this would just be the starting point. And we'll also talk about some more specific rules that we can use to try to make this test more sensitive to excursions away from the mean. Because we'll see that when using this 3 sigma limit, so I think one thing that you're getting at is this 3 sigma limit is pretty big, right? And so that excursion on day 18, right, where we saw the really high mean of the sample, that might indicate a problem, right? And we're just not sensitive enough to detect it. There are other methods to try to improve the sensitivity of this, and there are other control trial methods that could be used as well. Yeah, go ahead. In this case, n is 3. Yeah, so n is only 3 because, I mean, oftentimes it can be expensive, right? To run the test in the QC lab can be expensive, typically time consuming, right? Depending on what test is being run. And you have to pull products off the line. So depending on what you're making, you may not be able to sell that product, right? So n is not often going to be that large. right, on a given day. Yeah, so the question is, does it ever get skewed? I mean, if you had a process that had very high variation, then you could end up with unreasonably large limits on this process, on this control chart. And then, yeah, I guess you'd have to look at something else in the process that goes beyond just statistics. Or consider doing, having a larger number of samples collected per day or something. But again, economics and other things dictate how many samples you can actually run. Yeah.
Let me just find sigma as 0.18. That particular sigma, are you finding the standard deviation of like all 3 data points, or you take?
Yeah. So the question is, in the code, we use a standard deviation, a sigma of 0.18. So our first example here is when we know what the mean and standard deviation of the population should be. So as an example, let's say you're starting a new production line, right? So or you're restarting this production line after the holidays, right? You know, based on years of experience, or after a new piece of equipment came in, right? You know, after years of experience, the mean should be 10.5, the standard deviation should be 0.18, right? You have books of data to back that up. And so therefore you're going to use those, right? If you know what the process looks like when it's in control, you use those values. The next example is actually going to be the same data set, but let's say we don't know those. How can we estimate them? Okay. Yeah. Good question. All right. Other questions? Okay. So, I mentioned, so often going to be the case where we don't know exactly what the sample standard deviation or what the population mean and standard deviation are, right? So maybe we haven't been running this product line for that long. We only have 25 days of data, and we still want to know, is it likely that the process was out of control on one of those days? Or we're trying to set up a new control chart, and we need to estimate what the population mean and standard deviation are. We can do so from the data that we're given, and we just have to make the estimate from the data. So so it could happen when a process has been changed or a quality control analysis is just being started. So there are different methods here. We're going to focus on the method that is based on the measured standard deviations. There's an alternative method based on measured ranges, but we're just going to focus on the method based on standard deviations. So let's say that we have, so in our case, so we have a certain number of sample means. So we're going to say we have K sample means, in this case 25, because we're measuring for 25 days. Then our best estimate of the population mean, here it's denoted mu hat because it's our estimate of the population mean. It's the mean of our sample means. So it's just the mean of all, in this case, the mean of all 25 of those means. So it'd be the sum of all those X bars divided by 25. So just the mean of all our data, that's our best estimate of what the population average is. That should make sense, right? Where things get a little bit more complicated is when we're estimating sigma. So the sample standard deviation is not an unbiased estimator of sigma, because when we have a sample, this is related to the delta degrees of freedom, which we spoke about earlier on in the class. But whenever we're measuring a sample and we're trying to estimate the variance or standard deviation of that sample, we're trying to estimate the population standard deviation from just a small sample, we are essentially always going to be underestimating what the actual standard deviation is. And this can become an issue if we're trying to measure when we're applying this to these control charts. So the solution is that we have a correction factor that we apply in order to, so we're trying to find the overall population standard deviation from the standard deviation of a number of different samples. There's a correction that we apply. So for this, in this case, we're going to use that our estimate of the population standard deviation, sigma, is going to be the average of the sample standard deviations divided by a correction factor, AN. And the suggested form of that AN is based on this function here, which is called the gamma function. We haven't covered the gamma function in detail, and so we're not going to cover the gamma function in detail. So for now, we'll just take this as a correction factor on the standard deviation that allows us to make a better estimate of what the population standard deviation is. So in this case, that correction factor is about 0.886, right, or 0.89. So gamma, this is the gamma distribution. We've seen, so the exponential distribution is a special case of the gamma distribution. So if you remember back a number of lectures ago, we talked about the exponential distribution. It's also related to chi-squared distribution. But for this discussion, we'll just say that the gamma distribution is something that goes into computing this correction factor. So once we have that correction factor, that AN, we then estimate the upper and lower control limits in this form, where it's, so we use the overall mean of all of our X bars, right, as our estimate of the population mean. This is the mean of all of our sample standard deviations divided by AN. Again, that's our estimate of the population standard deviation. And then we're also dividing by that square root of n. So, so we can use that. We can apply this in order to make our estimates first of what the population mean and standard deviation are. So we get 10.4 and so we get 10.5 is our estimated our estimated population mean, which is very close to, or this 10.476 is very close to the 10.5 that we assumed previously. And we have an estimated, so the mean of all of our sample standard deviations is 0.15. So where this is coming from, so this is S bar, we have 0.15. That is the average. Let's scroll up. This is our data. For each sample, we computed the average of the sample and the standard deviation of the sample. This is for the sample of 3, right? So S bar is just the average of all the values in this column here. So for each day, we computed the standard deviation from that day, and then S bar is just the average of all of those daily standard deviations. Okay. Yeah. Is the estimate of the parameters always going to be more conservative than what the actual parameters are? It would be nice if that were true, but I don't believe you can guarantee that. Yeah. You know, it may just happen that you have, like by random chance, you have a sample that has a smaller standard deviation than average. You could actually address that, the probability of that using chi-squared statistics, but that's beyond the scope here. So in this case, we see that, just to come back to that, so the S bar was 0.15, and that is less conservative than what we expect from the sample was 0.18, 0.153 divided by 0.6. So, you know, our limits, our control limits, if we omitted that correction AN, our control limits would be too narrow, right? So we're attempting to correct for that with this factor AN that's based on that gamma distribution. But if you just take this 0.153 divided by 0.886, you end up with 1.173, so still smaller than that 0.18. And so it's not a perfect estimator. Yeah. In this case, our limits are a little bit tighter. So when we put that together, so this code puts that together. So we have our mean of all of the sample means, and our S bar is the mean of all of the sample standard deviations. Right, so that's these values here. And then we're going to use those in the formulas up above here, equations 9 and 10, incorporating that factor AN that we computed. We end up with our lower and upper control limits based on our estimation of those parameters, as shown here. And now if we prepare the same plot, we can see the plot of viscosity as a function of days. And again, we would conclude that all of our sample means were within control limits. But notice that because we have slightly tighter limits here, so we're estimating those parameters. We ended up actually just a little bit closer on that day 18, but we're still within the control limits. Okay, so we'd still say that this process appears to be within control. Okay. All right, any questions on that so far? Okay, so we'll say just a few words about performance of this for detecting actual excursions away from the control values. So we've shown that the 3 sigma control chart is effective at giving few out of control signals, right? It gives us few out of control signals when the process is in control, right? So we have, if the process is currently in control, we have only about a 0.002, so this is about a 0.3% chance of getting a signal that's telling us erroneously that the process is out of control, right? So we have a very low probability. If the process is in control, we have a very low probability of it falsely telling us that the process is out of control. But this comes at a cost, which Connor noted, which is that it means that this test is less sensitive at detecting when something actually goes out of control, right? So this is the other side of this, the other side of this, the other type of error that we can have. So the text that we're basing this on notes that the probability that an out of control process will be detected by the control chart is a function of delta, which we'll define as the number of standard deviations by which the process is out of control. So what that means is, like, let's say we have this process running and we're now out of control. Something has happened. The winds have kicked up out of the west at the Micron plant, right? Or the raw material that we're using to produce, or one of the materials that we're using to produce the oil is coming in with a higher than expected molecular weight or something. And so our process is going to run out of control. We can think of one way to define how far out of control it is in terms of delta, where we'd say the new mean, right? Let's say our out of control mean is the in control mean plus delta times that sigma over square root of n, right? So if we're out of control by a certain amount, delta. And we can use this then to estimate how sensitive our control chart is going to be at picking up an error of size delta. Okay, so that's why we write it this way, so we can make kind of a general statement. So in this case, so this chart here, this Excel spreadsheet here defines the probabilities. So if we look at for a delta value of 0.25, right, meaning we are a quarter of a standard deviation out of control, then the probability that our process looks in control, that's what this beta is 0.9936, meaning that we are going to be very, very insensitive to that kind of an error. If we have to go all the way up to a delta of 1.5, meaning we're 1.5 standard deviations away from the expected mean before we have a 50-50 chance of detecting the sample as being out of control. Does that make sense? So this is exactly what you were talking about, Connor. This is the fact that we set our limits at 3 sigma means that we are not often going to be down at the assembly line or the product line trying to diagnose a problem that doesn't exist, right? And that's good. But it also comes with it the cost that we have lost the ability to to detect when the process is actually out of control. And we can see that as we go to delta of 3, then we end up having a very high probability of actually detecting it. So what this leads to is oftentimes supplemental rules that might be used on top of this. So as I mentioned, this control chart and this kind of 3 sigma control chart is, again, one of the more basic tools we might use in assessing quality control. But there are many other methods for assessing when a process is out of control, some of which may be just supplements to this rule, supplements to what we see on the control chart. So one example, some examples that are given here are just based on the fact that if our process is truly in control and the changes that we're seeing within or the variation that we're seeing in the process is just due to random noise or random variation from day to day or from run to run, then we are unlikely to see, if we see excursions on the same side, or we see errors or deviations from the overall mean that are systematically on one side of that mean, or systematically large on one side of the mean, then it is unlikely, or it's less likely that those are due to random chance. So as an example, if we're tracking the mean viscosity of motor oil that we're producing, and all of a sudden something has changed, like we have a different molecular weight of one of the incoming products that's going to raise the viscosity of our final motor oil, then we will become more likely to see multiple excursions or multiple errors that are, for example, larger than the expected mean. And so that's where these supplemental rules come from. So one is we might look for 2 out of 3 successive points falling outside of 2 sigma limits on the same side of the center line, right? So 2 out of 3 days we see, if 2 out of 3 days we see something greater than 2 sigma away from the mean, above the average, we might signal that there's a problem. Or 4 out of 5 successive points falling outside of 1 sigma limits, or 8 successive points falling on one side of the center line. These are examples of the types of rules that you might build on top of it. So to go up here, that first rule was that we had, was it 2 out of 3 successive points falling out of 2 sigma limits. So on its own, this single excursion up here doesn't look like it's evidence of a problem, right? By our reading of the control chart. But if we had seen, for example, one of these 2 measurements also reading high, more than 2 sigma above, then we might take that as evidence of a potential problem that we need to track down. Does that make sense? But these are just, again, some examples, and we're really just barely scratching the surface of quality control and how you would use this, put this into practice. All right, any questions on this? Control charting for sample location. All right, so we're going to end a little bit early today. On Wednesday, we're likely not going to end that early because we're going to look through lecture 22. We're likely start on 23 to give us more time for review. And I want to go over that quiz. So on Wednesday, we'll be here a little bit longer. All right, thank you all.